In this video, we're going to take a look at Gaussian elimination and row-reduced echelon form. So the goal is to take a system of linear equations and convert it into a matrix that's easy to use. Once we do that, we will manipulate it so that it's really easy to read off the answers to the system of linear equations. So we start out by creating an augmented matrix for a system of linear equations. Now, when we create an augmented matrix, what we're going to do is we're going to make sure our equations are lined up in the following way. We'll have, just like when we dealt with the elimination method, we'll have our x values in line, our y terms in line, and then we'll have equal signs, and then on the right-hand side of the equal sign, we'll have our constants. So 3x minus 4y equals 11 becomes the first row in the augmented matrix of 3, negative 4, 11. Negative 2x plus 6y equals 12 becomes the second row in our augmented matrix of negative 2, 6, 12. So each column represents a variable. Each of the first two columns represent a variable. And the third column represents our constant number. Now, a lot of times people will write a vertical line where the equal sign is. Sometimes people leave this off as well, but sometimes people write it, sometimes people don't. So each row represents an equation. The first two columns represent a variable, and then the last column represents our constant number. So let's do that for this example. Let's create an augmented matrix representing this system of linear equations. Push pause on the video if you'd like to try this on your own. Since this system has two equations, it'll have two rows. Since we have two variables and then a and then a constant, we'll have 3 total columns. Our first row will be 5, 10, and 25. Our second row will be 7, 6, and 3. I obviously didn't write the vertical line in between the column representing the terms with y's and the column representing the constants. So I didn't write a vertical line in this case. But there you go. That would be the augmented matrix for this system. Here is another example that asks me to create an augmented matrix representing the system of linear equations below. We have x1 minus 2x2 equals 10, 3x1 plus 5x2 equals 8. Again, if you'd like, you can try this on your own. Just push pause on the video. In this case, everything is aligned. So the variable of x1 is in the front there, then x2, then the equal sign, then the constant. That works both the same in both equations. So our coefficient of x1 is 1, coefficient of x2 is negative 2, and our constant on the right-hand side of the equation is 10 in the first equation. That means the first row of my augmented matrix is 1, negative 2, 10. My second row is going to be 3, 5, 8. Notice that in this example, my variables were x1 and x2. x sub 1, x sub 2, that just means the first x value, the second x value. In the previous example, my variables were x and y. It doesn't matter what the variables are. You could have just as easily called them variable A and variable B as variable X and variable Y. So as long as we're consistent with what we call our variables, we're just fine. Let's do another example. Here's an example where we have 3 equations and 3 variables. Go ahead and try to create the augmented matrix that represents this system of linear equations. Push pause on the video if you'd like to try that on your own. Just like we did in the other cases, I have things lined up so I can just read off the coefficients. In the first equation, we have 1x1 plus 5x2 minus 9 times x3 is equal to negative 17. So the first line is 1, 5, negative 9, negative 17 in the augmented matrix. Now in the second equation, we have a 2 is our coefficient of x1, but notice x sub 2, there is no x sub 2 term. In the augmented matrix, that means we need to plug in a 0 for the x sub 2 coefficient. So it's like having 2x1 plus 0x2, and then plus 1x3 is equal to negative 6. And in the last row, we're going to have 4 as the coefficient of x1, negative 6 representing the coefficient of x2, 12 as the coefficient of x3, and then positive 2 as my constant on the right-hand side. By the way, if the equations we're given don't have all of the variable terms on the left and the constant term on the right, then simply move things around until we get that look. We want all of our variable terms on the left, all of our constant terms on the right, and then I can put it into an augmented matrix. Now remember, x1, the coefficients of all of our x1s are in the first column. The coefficients of all of our x2s are in the second column. In the third column, it's the coefficients of x3. And in the fourth column, it's our equal to constant number. So we always want that scenario where the columns are representing the same variables. And then on the right-hand side, we have equal to our constants. So the very right-hand side column represents our constant numbers. Now, once we have our augmented matrix, the goal is going to be to use Gaussian elimination. And all that means is we're going to do a process where we convert that augmented matrix into systems of linear equations with the same output, the same answers. So we're going to use a few properties on the augmented matrix, and that will change the augmented matrix into a matrix that has an easier form to read the answers. Now, the tools we can use with Gaussian elimination are as follows. There's 3 main ones. We can multiply a row by a constant. By the way, if we multiply an equation by a constant on the left and the right, That doesn't change the answer to the equation. We can swap rows. Swapping rows is like swapping the order that the equations come in, and that's not going to change any answers either. And then the third one is that we can replace a row with two rows added together. And because we can also multiply by constants, sometimes what we'll do is we'll multiply by constants and then add two rows together in the same step. By the way, that's like doing an elimination method where we add two equations together and then we get a third, and then we replace an equation. So all of these processes have equivalent algebraic processes when we try to solve a system of linear equations. Now, the goal is to do this Gaussian elimination until we get our matrix, that is our augmented matrix, in what's called row-reduced echelon form, or in short, RREF. So when do we know that a matrix is in row-reduced echelon form? Well, row-reduced echelon form is going to have three properties. The first property is that the lead non-zero entry of each row is 1. So we might have some zeros in a row, and then the actual first number that's not 0 is going to be a 1. These are going to be called pivot positions, where we have a 1 as the lead entry of a row. These pivot positions are going to have zeros above them and zeros below them. And then we're going to have a stair-step effect with pivot positions. So we're going to start, our first pivot position is going to be the highest left hand. And then we're going to go down and to the right to hit our next pivot position. And then we move down and to the right to hit our next pivot position. So those lead non-zero entries where they're 1s are the pivot positions, and then the pivot positions start in the upper left and move down and to the right, down and to the right. And we'll get more and more pivot positions. So the following matrices are in row-reduced echelon form, which we're always going to call RREF in this class. So notice this first matrix here. We have a 1 that is one of the pivot positions. When I move down, there's a 0 below it. Notice that the next pivot position is down and to the right. That next one is another lead entry. This is what we mean by stair-step effect. We go down and to the right to hit our next pivot position. Now I can't go down anymore, so we're done here. So there's zeros below the 1s, zeros above this 1, and the pivot positions of those 1s move down and to the right. That's the same thing in the second matrix as well. We have 3 pivot positions. All of those are the lead entries of our row, which are 1s. There's zeros below each pivot position and zeros above each pivot position. And in the case, we might have some zeros above and some zeros below in that middle case. And then we have the stair-step effect where I go down and to the right down and to the right to hit each next pivot position. Now it turns out these matrices are also in row-reduced echelon form. They look a little bit different than the first ones, but they still have that same phenomenon. We have a pivot position in the upper left, zeros below it, zeros above it. When I move down and to the right, the next non-zero is going to be another pivot position of coefficient 1. Notice that 0 is above that 1. So this is in RREF. This 2, this right-hand matrix, is also in row-reduced echelon form. I have a pivot position here. Notice as I move down and to the right, there's no lead coefficient, there's no non-zero term, so all the terms are just 0. Now zeros have to be below and above the pivot positions, but any other positions, it really doesn't matter if zeros are below and above. In this case, it was. So it's perfectly okay to have 1, 3, 8, and then a row of zeros. Oops. Here we have that same case. We have 1, move down and to the right, we get another 1. We have no other pivot positions. We just have 2 pivot positions. There's zeros above and zeros below each of the pivot positions. And again, as you move down and to the right, that's how we encounter our pivot positions. In that last row, it's all zeros, so I don't encounter any pivot positions. Now, these 2 matrices are not in row-reduced echelon form. I have a pivot position here at the 1 spot, this upper left-hand spot. As you move down and to the right, this 5 should be a pivot position, but the numerical value is a 5 instead of a 1. So that's not an RREF yet. Also, this is not an RREF because if this pivot position in the upper left-hand corner in the 1, 1 spot is 1, you move down and to the right, you hit a 1. But if you notice that above this pivot position, we have the number 2 and not the number 0. And so because this number 2 is here, this is also, the second matrix is not in row-reduced echelon form. So let's refresh our memory. We want to use Gaussian elimination to force this row-reduced echelon form. The tools we're going to use are going to be the following. We're going to multiply a row by a constant number. We're going to swap rows. We're going to replace a row with 2 rows added together. And again, a lot of times I'll multiply the 2 rows by a constant and then I'll add them together. And we do that until we get to the row-reduced echelon form. So let's do an example by hand where we're going to force row-reduced echelon form. Here we have 2, -5, -28 in the first row, 3, 1, 26 in the second row. All right, so if we're doing this by hand, one key thing is that the notation that we use generally is a little bit tricky. There's different types of notations. A lot of times I just use arrow notations. So what I do is I start by creating a pivot position. I'm going to create that in this spot right here, the upper left-hand spot where this 2 is. To be in row-reduced echelon form, I need that pivot position to be a 1. So I need to multiply that entire row by 0.5. When I do that, what I end up with is I end up with 1 and then negative 2.5 and then negative 14 as my first row. Now my second row does not change. So it's going to be exactly equal to what it used to be. So that's step 1. Then I take this matrix here, the one I get, and I'm going to force a 0 to be underneath this initial pivot position. So I'm going to force a 0 to be in this 3 spot. The way I do that is by adding up 2 rows. I'm going to take the first row times a negative 3 and then add it to the second row and then replace that second row with the result. Here's how I will write the notation. So here's how I write the notation. I take the first row times negative 3, the second row times 1, and then I combine those two. A little bit of a bracket there sometimes helps. And then I replace that summation. I replace the second row with that summation. That's why the arrow is going into the second row and not the first row. There's nothing changing in the first row. First row stays the same, so there's nothing changing in the first row. And then the second row, I get negative 3 times 1 plus 3 times 1, which is 0. Negative 3 times 2.5 plus 1 times 1. So negative 3 times negative 2.5 is 7.5. 1 times 1 is 8.5. So 1 times 1 is 1. When I add those, I get an 8.5. Negative 14 times negative 3 plus 26 times 1 gives me a 68. Hopefully everybody understands where I'm getting that. Let me, I guess, write down an intermediate step. We're taking negative 3 times negative 2.5, and then I'm adding 1 times 1. And that's where I'm getting the negative 8.5. Or excuse me, not the negative 8.5. And then 68 is coming from negative 3 times negative 14 plus 1 times 26. And that's where I'm getting a 68. So there we go. Now I have a 0 where I want it. However, I don't have what I want with that 8.5. I want a 1 because that should be a pivot position. So I'm going to force that to be a pivot. I know that's a pivot position now because move down and to the right, first non-zero should be a 1. So I'll force that to be a 1 in the same way I forced the 2 to be a 1 in this first example. So I'll just multiply this second row by the inverse of 8.5. In other words, 1 over 8.5. And then get a new matrix. Let's go ahead and do that. So I take this matrix, I put it down here, and then I multiply the second row by 1 over 8.5. and I replace the second row with that new. Now, multiplying 0 by 1 over 8.5 is not going to change anything. Multiplying 8.5 times 1 over 8.5 gives me 1. And then 68 multiplying times 1 over 8.5 actually gave me an 8. So I get 0, 1, 8 in my second row. Now this 1 is a pivot position, so I want to create a 0 above it. So I'm going to do that by multiplying the second row by 2.5 and adding it to my first row. This is why we wanted to have a 0 here before we tried to create a pivot position, because now when I start adding rows together, 0 times anything is 0. Plus 1 just becomes plus 1. So that's what I'm going to do. In a very similar way to this second step, I'm going to make a 0 above this pivot position of 1. Let me write that down. So here we go. I've written that down. I'm going to multiply the second row by a 2.5 and then add it to the first row multiplied by 1. If I multiply the first row by 1, I get 1 times 1. If I multiply then I get 0 plus times 2.5. So 1 plus 0 basically is my first entry, which is a 1. My second entry is going to be negative 2.5 times 1 plus 1 times 2.5. Notice that gives me a 0, which is exactly what I wanted. And then my third entry is going to be a negative 14 times 1 plus 8 times 2.5. Well, that can be calculated. And when I calculate that, I get a 6. Now I have exactly what I want. I have the 1s in the pivot positions, 0s above and below the pivot positions, and this stair stepper effect. So essentially what we're saying is that this matrix is the row reduced echelon form of my original matrix. Now these matrices are not equal. What I'm saying is that the row reduced echelon form of the first matrix is this. And the nice thing about row reduced echelon form is that if this stood for a system of linear equations with x variable in the first column, y variable in the second column, and constant in the third column, then this row reduced echelon form of a matrix is telling me essentially that x plus 0 y equals 6 and 0x plus 1y is equal to 8. So the row reduced echelon form of the matrix essentially gives me my answer. Now, doing this by hand can be quite tedious, especially in really large matrices. Obviously, here we had 4 steps: force a pivot position, get 0 underneath of it. Once we did that, then force another pivot position to be 1, get 0 above it. You could imagine if you did a 3-row matrix or a 4-row matrix or a 5-row matrix, that every pivot position is causing two steps because I have to make the pivot position 1, and then I may have to make everything below and above it zeros. And in a 3 matrix case, then I would have to make lots of zeros. If I had a matrix with 3 rows, there'd be a lot of zeros. So doing this by hand would take quite a lot of time on big matrices. But there's a really good, nice thing is that if you have a TI-84 calculator, it turns out there is a way to do Gaussian elimination and just ask the calculator for the row-reduced echelon form. And when you do that, all we have to do is take RREF of this matrix, and our calculator will spit back the row-reduced echelon form of that matrix. On other calculators, you can do that as well, but the TI-84 calculator, we'll see how to do that in an additional video. Okay, I'll have a really short video on how to force row-reduced echelon form with the TI-84 calculator. So let's go ahead and do that. Let's use Gaussian elimination to force row-reduced echelon form, and we'll be using the calculator in this case. Now I'll talk through how we do the RREF of this matrix. Basically, on the TI-84, you would do your matrix menu, which is second, and then the X inverse button. And then you'd scroll over to Edit and click on Matrix A. You would input 8, 3, -2, 4, 1, 2 into Matrix A. And obviously, this has 2 rows and 3 columns. So you have to state that this matrix is going to have 2 rows and 3 columns. Once you have this matrix input, then you go into the matrix menu, and in the math section of the matrix menu, as you scroll down, you'll find an RREF. And so I just I hit that, and then I go back to the matrix menu and I get A. So I do RREF of matrix A, and then I hit enter. And then my calculator does all of the hard work. It does basically all 4 steps we did by hand in the last example in about a half of a second. So we get this matrix that is in row-reduced echelon form. 1, 0, 2, 0, 1, -6. And if this represented a system of linear equations, we'd know that x is equal to 2, y is equal to -6, if those were my variables. So the matrix menu on the TI-84 allows us to shorthand that whole process. By the way, that process could have been done by hand, like I said, in the same way we've done before. Again, what I would have done is I would have multiplied by that first row by 1/8. When I did that, I'd get this. Then, in order to make the 4 into a 0, I'd multiply the first row by -4 and then add it to the second row. That would replace the second row. And so I'd get a 0 there. And then I'd also get -1/2 and 3. I'd multiply the second row by a -2 to get a pivot position of 1. And I get 0, 1, -6 in the second row. And then, in order to get a 0 above this pivot position of 1, I'd have to multiply the second row by -1/3 and add it to the first row, and then replace the first row with that sum. That would give me 1, 0, 2 in the first row and 0, 1, -6 in the second row, which is exactly what we got using our calculator. Again, it was just much faster by using the calculator. Here's another problem to try using your calculator. Here we have a 3x4 matrix. This could represent a system of linear equations with 3 equations and 3 variables, for instance. We can use RREF on our calculator to force this matrix into RREF, or row-reduced echelon form. Let's go ahead and try that. Push pause on the video if you'd like, and then in a couple of seconds, I will show you how it's done. Now, once again, I'm using the calculator to do this. So I'd go in the matrix menu and then edit matrix A. This matrix is 3x4, so make sure we set it up as a 3x4 matrix. After I've done that, then I go back to the home screen and I go into the matrix menu, Math, RREF, and then I make sure I'm doing an RREF on matrix A. Once I do that, my calculator gives me the answer that I would like. The row reduced echelon form of this matrix is 1, 0, 0. I'll write them all in. So 1, 0, 0, 3, 0, 1, 0, 4, and 0, 0, 1, -2. And that's it. That's the row reduced echelon form. By the way, there would have been a lot of steps to try to get this into row reduced echelon form if I had to do this by hand. We already have this pivot position of 1, but then I need to make both this -1 into a 0. That would be one step. And then the 2 I'd have to make into a 0 as well. That would be another step. Then I'd make this value equal to 1, make sure there's a 0 above and a 0 below. Then I'd make this value equal to 1, make sure there's zeros above. So it would be quite a few steps. And with our calculator, we can do that in a very, very short period of time. By the way, I'm using a TI-84 calculator. There's all kinds of other programs that you could use which have RREF embedded in them. So a lot of different math software has that. Now, previously, we started with a system of linear equations. So we had dealt with an example 1 earlier where we had to write an augmented matrix, or excuse me, where we had 5x plus 10y equals 25 and 7x plus 6y equals 3. Let's go ahead and write an augmented matrix representing that system of linear equations and then use row reduced echelon form to solve that system. So here we go. From example 1, we had already created the augmented matrix of 5, 10, 25, 7, 6, 3 that represents this system of linear equations. So that happened in example 1. That was what we did in example 1. And now we're trying to solve this using RREF. So all I would do is I'd make that augmented matrix, matrix A, in my calculator, and then RREF that matrix once I do that, I get 1, 0, -3, 0, 1, 4. So 1, 0, -3 is in row 1, 0, 1, 4 is in row 2, and that means my x value has to be -3 and my y value has to be 4. That's what this reads off as. 1x plus 0y equals -3. That's just x equals -3. And then the second line becomes 0x plus 1y equals 4. So y equals 4. And that's my solution. My solution to this system of linear equations is going to be when x is -3 and when y is equal to 4. We can write that as an ordered pair if we'd like. You don't have to write that as an ordered pair, but that's the solution to this system. And you can check that if you plug in a -3 and a 4, -3 into x, 4 into y, if we plug those in, then we get both of these equations giving out a true statement. Again, you can check that on your own if you'd like, but it does work. Let's do the same thing for example 8. Now, this was our previous example 2. So this was previously example 2. We had found the augmented matrix that represents this system of linear equations. Now I want you to use row-reduced echelon form to solve this system. Push pause on the video if you'd like. In a couple of seconds, I'll show you how it's done. All right, so let's do this. First off, the augmented matrix we found earlier as 1, -2, 10 as the first row, 3, 5, 8 as the second row. I'm going to use the row-reduced echelon form to solve that. So all I have to do is ask my calculator to give me the row-reduced echelon form of that matrix. Now, when I do that, it's going to have the same dimensions. It's going to have a pivot position in that upper left-hand corner. The first row becomes 1, 0, +6. The second row becomes 0, 1, -2. And that means that the solution is that the x1 variable needs to be equal to 6, and the x2 variable needs to be equal to -2. Sometimes people put this as an ordered pair as well. And if you do put this as an ordered pair, usually the x1 comes first. So if you're writing this as an ordered pair, it'd be 6, -2. And that's it. So the whole thing comes down to being able to force an augmented matrix into row-reduced echelon form. Once we do that, we can read off the solution very easily. Let's do the example we had earlier, where we had 3 equations and 3 variables. We already wrote the augmented matrix for this system of linear equations in example 3. Now let's use RREF to solve this system. Once again, if you'd like to try this on your own, push pause on the video. In a couple of seconds, I will show you how this problem is done. like I said, we already got the augmented matrix for this system of linear equations. The augmented matrix had row 1 of 1, 5, -9, -17, row 2 of 2, 0, 1, -6, and row 3 of 4, -6, 12, +2. And so to solve the system of linear equations, I would simply take the row reduced echelon form of that augmented matrix. And when I do that, well, let me type in each thing. I would get 1, 0, 0, -4 in the first row, 0, 1, 0, 1, that is +1, in the second row, and then 0, 0, sorry, 1, and 2 in the third row. So now I can read off my solution. My variables were x1, x2, x3. So this means that x1 variable is equal to -4. The x2 variable is equal to 1. And the x3 variable is equal to 2. Or if we had to write this as an ordered triple, we would write it as x1, comma, x2, comma, x3. So in our case, that's -4, 1, 2. Again, this saves a lot of time because if we are able to program this into our calculator or do this on some other computer program that helps us with math, then this is a lot faster than trying to do the elimination method or than trying to utilize substitution or trying to do Gaussian elimination by hand. So this can be a very effective and efficient method. And this is what the next slide says. The advantage is that it's really easy to program this process into a computer. And we have that process already programmed for us into a TI-84 if you have it. In other math programs, it's like a pre-programmed thing, so you can do it in other math programs as well that allow you to deal with matrices. And so it's a very fast method for solving a system of linear equations. So all of the linear equations, systems of linear equations that we did earlier, we could solve it using RREF as well. And so the word problems that we did using systems of linear equations, all of that stuff could have been done by using the row reduced echelon form of an augmented matrix. Now, before we end, I want to show you a couple of things. These are sort of the weird scenarios that could happen. So let's take this example 10 and write an augmented matrix, put it into row reduced echelon form, or take the row reduced echelon form of the augmented matrix, and then decide what that means for my solutions to this system of linear equations. If you want, push pause on the video and you can try it on your own. Otherwise, I will do this in a couple of seconds. All right, let's go ahead and do this one. So my augmented matrix is going to be 1, -3, 7, and then -2, 6, -10. So the first row is 1, -3, 7. The second row is -2, 6, -10. Now I'm going to take the augmented matrix and I'm going to row reduce it. So I'm going to take the row reduced echelon form of that augmented matrix. And when I do that, I get out, well, I'm going to do it with my calculator. So I end up getting 1, -3, 0. And then in the second row, I get 0, 0, 1. Now, if you think about that, that means x minus 3y has to be 0. And what's really important is that the second equation tells me 0x plus 0y is equal to 1. In other words, that second equation tells me 0 is equal to 1. That's obviously not true. That's a false statement. I'll just write false in there. And what that means is that this is the scenario where we have no solution to our system of linear equations. When we get a row that looks like 0 equals 1, then that tells me there's no solution to that original system of linear equations. So this is the weird case. Most cases end up like this, where we have one unique solution, one ordered pair or ordered triple. But in this scenario, we end up with a false statement. So therefore, I know that the system of linear equations has no solution. So example 10 was a system of linear equations which had no solution. Example 11, I just changed one number. I'm going to change that -10 to a -14 and see what happens. I'll do this one really quickly. So the augmented matrix has first row of 1, -3, 7, second row of -2, 6, -14. When I plug that into my calculator and do a row reduced echelon form of that matrix, I get first row of 1, -3, 7, and a second row of 0, 0, 0. And what this means is that x minus 3y is equal to 7, and 0 is equal to 0. That's my two equations from my row reduced echelon form of that matrix. Now 0 equals 0 is a true statement, and x minus 3y equals -7 is a line. So we get a true statement and a line, which means that the number of solutions that I have is infinitely many. And moreover, all of the solutions to this system are points on this line. So there are infinitely many solutions to this system. Infinitely many ordered pairs that work on this system, and the ordered pairs are all going to be the ones that are on this line. So that's what it tells me in this case. So there you go. Augmented matrix. We can solve a system of equations by creating an augmented matrix, putting that augmented matrix into row reduced echelon form. In most cases, I can just read out the solution. And then we have a couple of unique cases in which we end up with the infinitely many solutions or no solutions scenario. So that's how we can use Gaussian elimination when solving a system of linear equations, or to have matrices, in particular augmented matrices, help us solve systems of linear equations.